Hello students, welcome back. So now we are going to be talking about Seaborn's pair plot library. This one is primarily used when you want to display multiple numerical columns on the same plot. So for example, take a look at this one. In this case, you have like these are your numerical columns. I have build length, build depth. You have all these values over here, all these columns, and then you have another columns over here. So this way you can identify some linear trends or non-linear trends, stuff like that using this pair plot. So let's do some examples. So this way we can understand that. So I'm importing my Seaborn. I'm also importing my Matplotlib library. So Seaborn provides you this iris dataset. So that's the one I'll be using on this session. So let's load our iris dataset and let's print out few numbers of the iris dataset. So this is sepal length, sepal width, petal length, and petal width, and this is a species. So there are three different types of species. You have Setosa and you have versicolor and virginica. So based on the different type of species, each one of them has its unique sepal length, sepal width, petal length, and petal width combinations. Okay, so let's do pair plot. In this case, I'm specifying my data equal to iris, and let's do pair plot on this. Let me decrease the size of the screen so it's a little bit more visible. So in this particular instance, you can see the numerical relationship between different numerical columns. So in this case, let's look at one of the column. Let's look at this one right here. So in this particular one, this is the relation between petal length and petal width. Okay, and you can see that as your petal length goes up, your petal width, it also goes up. All right, what about this one right here? Let's look at this one. This is a relationship between sepal length and sepal width. And in this case, I don't see much strong linear relationship. You can see that like it's basically a spherical in shape. So anytime when you get your data point like this in spherical in shape in your scatter plot or your pair plot, generally that's an indication that there is not a strong linear relationship. So in this particular instance, I can safely conclude, let me increase the size of the screen. Okay, so I can safely conclude that there is a strong positive linear relationship between petal length and petal width. We just saw that. That was this one, petal length and petal width. And also there is a weak linear relationship between sepal length and sepal width. That would be this column right here, this particular diagram right here. Okay, now you can also separate them based on the species. So I'm doing the same thing. I'm calling pair plot inbuilt method. And this time I'm specifying my U equal to species. So U should be categorical in nature, by the way. So when I plot this thing, now this is the same plot, but now it's going to separate. It's going to put different colors to different data points based on what the species is. If it's a Setosa, it's going to put blue color. If it's a versicolor, it's going to put orange. And if it's a Virginica, it's going to put green. So by looking at this, you will see some interesting patterns right here. For example, let's look at this one right here. You can clearly identify Setosa very easily. Setosa would be blue. So you see these blue clusters over here. So that should tell you that anytime when you have a petal length between 0 to maybe 2 and your petal width is between 0 to maybe 0.6, it's very likely it is going to be a Setosa flower. And so you can identify that from here. Also, same thing, you can draw similar conclusion from here. But over here, you cannot do that. You can see that there is a strong overlap between versicolor and virginica. You see the points are overlapping. So it's hard to distinguish your versicolor and virginica if you use sepal width and sepal length. On the other hand, if you use petal length and petal width, then you can like kind of distinguish your virginica from versicolor, because your virginica, let's see, virginica is green. So virginica petal length will go from this number, I would say from 4.5 to maybe 8. On the other hand, the petal width is going to go from this number, that would be, I would say, 1.5, 1.5, yeah, let's go with 1.5 to 2.5. So this way you can identify each one of them. Okay, so this is the conclusion I wrote over here. The Setosa can be easily identified using petal length and petal width. For Setosa, the petal width is going to be between 0 to 0.6, and your petal length is going to be between 0 to 2. We just saw that over here. All right. Now let's understand this through another data set. In this case, I'm using penguin data set. So let's print out the penguin data set, and this is the species, island, bill length, bill depth, flipper length, and body mass G, and the gender, what the gender is of that of the penguin. So in this case, I'm plotting my pair plot again of penguin data set, and by looking at this, let me decrease the size again. Okay, by looking at this, you can see that there is a strong linear relationship between these two variables. That would be your flipper length and your body mass G. So when your flipper length goes up, your body mass G also goes up. On the other hand, I don't see much strong linear relationship between these this one right here. That would be your build depth and build length. So I don't see much strong positive relationship between these two variables. Okay, so likewise, you can draw similar conclusion by looking at each and every plot over here. Okay, now let's say you want one thing you notice over here is that this picture right here is same as this picture. Likewise, this image is same as this image, and that's because this is like a symmetrical distribution. This is a symmetrical plot. So you really don't need this part right here. This one you really don't need this information. You can actually figure out everything from the lower side. So in this case, you can do that corner equal to true. If we just want to plot just the corner part, just do SNS pair plot penguins and put corner equal to true. That's only gonna plot the corner ones, the one below the diagonal, not above the diagonal. So this way you can actually draw the same conclusion. Okay, then what if you want to see the KDE for your diagonal? You can do that too. So this is your same diagram. Let me decrease the size. So this is the visual diagram of this data right here, this one. And if you look over here, you see there's a strong linear relationship. And if you come down, you're going to see a strong linear relationship over here. This is one of the characteristics of this data set, sorry, of this particular plot. And by looking at this by putting this kind equal to KD equal to true, I'm saying that my diagonal, okay, I want the diagonal to be in kernel density estimation curve. So by looking at the diagonal, you can see how your data is spread around, spread out. Okay, then you can also put some species over here for penguin. So let me just increase the size more. So in this case, my data equal to penguin, and in this case, I'm putting u equal to species. This is my category right here. So category, all right. Okay, and let's plot this. So in this case, by plotting this, you can see a few interesting things. Let's see what conclusion can we draw. Well, this green one is isolated by itself very easily. So anytime when your build depth is between this number to this number and your body mass G is between this and this, then you can identify that as the green ones, and the green ones would be Gen 2. So yeah, so you can see that the green colors, the green the Gen 2 ones, they are able they are pretty much like you can identify them easily. They are clustered like separately from the rest of them. So observation easy to separate ideally using build depth and body mass. So your build depth, let's see, where's my build depth? Build depth is over here and body mass G is over here. Yeah, I clearly identify them easily. I can separate that. But you cannot separate your ideally with chin strap when you're using build depth and body mass G. You cannot, because there's a lot of overlapping happening. But you can separate them if you use this plot right here, because over here there's less overlapping. Okay, so this way you can actually separate certain data points and certain species. So I hope this session helps. Thank you.